Good afternoon, and welcome to today's Electronic Design Webcast. Our topic today, runtime provisioning of IoT endpoints with cloud credentials, sponsored by Texas Instruments and Amazon Web Services. I'm Bill Wong, Senior Content Director with Informance Design Engineering and Sourcing Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. Additionally, we welcome your question during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your question into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. Now let's meet today's speakers. Nick Letheby works on IoT ecosystems solutions at TI's Connected MCU organization. Richard Elberger is a Global Partner Solutions Architect in IoT at Amazon Web Services. You can learn more about our speakers by clicking on the blue speaker bio widget on your console toolbar. Now let me turn things over to our presenters. Gentlemen, the floor is yours.
Hi, this is Nick Letheby from TI, and I'll be presenting the initial part of the presentation for handing over to Rich later on. The first thing we're going to discuss is what secure provisioning is and look at a couple of generic approaches to achieving it before we do a deeper dive on both the device side and the cloud side of a specific implementation based on TI's SimpleLink Wi-Fi MCUs and the AWS IoT service from Amazon. Provisioning is the process of providing the appropriate credentials that a device requires to connect to a network. If we take a very simple example, you want to connect your phone to a secure Wi-Fi network. Your phone will obviously show you the network and ask you for a password. That password is the appropriate security credential. You enter it into your phone, it stores it. From then on, your phone can connect to that network automatically every time. In IoT device network, we're looking not so much at just connecting to the home Wi-Fi network, but how does it connect up to its network, which is a cloud-based service, and there'll be a cloud-based security credential it needs to obtain to connect into that service. When considering some of the goals of a provisioning service, we need to think of things obviously like security, with the issue being how do we prevent clones or unauthorized devices from joining the network, and how do we secure the network from potential attacks by hackers. The second issue, as we'll cover later, is that security can add cost to IoT devices, and we'll look at how that can be potentially eliminated and what those costs are. And finally, user experience must be good. So you don't want to have some very complicated provisioning process where it takes a long time to add a device. They have to call up tech support, and everything gets very complex and expensive for the user. So what type of security credential is required by an IoT device? Well, IoT device networks are obviously based on the internet, which runs TCP/IP, and then this general end-to-end security protocol used in TCP/IP networks is something called TLS. You may be familiar with it also as called SSL from earlier iterations. Now, a TLS requires that if you want to authenticate a client joining the network, it must have a certificate. So the credential we need to get down on the IoT device is a certificate. There's a couple of general approaches that can be used. One of this certainly commonly used today is during the manufacturing process, put the certificates on the IoT device. This can get pretty expensive for a number of reasons. To begin with, each IoT device has to have its own unique TLS certificate. So therefore, those certificates have to be individually placed on each device. And there's typically really two ways that can be done. One is that you can go out and purchase or use a third-party service to get secure elements, which are dedicated chips that then come pre-installed with a certificate and a private key. And then that chip is simply put down on the device. Obviously, that's adding to your bill of materials. The second approach is to have a secure manufacturing environment where you have the appropriate equipment to manage private keys and the appropriate security that they can't leak out to other parties. As you can imagine, both these approaches end up adding costs to your IoT device, and generally it's not easy to use a low-cost manufacturer for high-trust activities like managing secure keys. An alternative approach is to use some certificate signing requests, and we're going to use the abbreviation CSR going forward in the rest of this presentation. And this allows the certificate to be added during runtime. Now, how a CSR works is that the IoT device will boot up and it will generate and sign a certificate signing request. That CSR is now sent up to something called a certificate authority, a server, which then checks that there's a valid key in there in the request, and then issues the certificate down to the IoT device, which can then use that certificate to connect to an IoT service that's going to require device-side authentication. The CSR approach has two obvious advantages. One is we're eliminating the need to manage and inject certificates and the associated private keys during manufacturing, which enables a much lower cost manufacturing approach. And it's also easy to use from a user perspective. It's all automatic and transparent to the user. The CSR-based approach does have a couple of prerequisites. The first is that to generate a CSR, the IoT device has to have a public-private key pair. Now, you can avoid the costs of managing private keys and their associated security by simply using a wireless MCU that has a pre-burned key pair in it. The second issue is you need some additional form of device identity on the IoT device. This is because a certificate authority will issue a certificate to any device that has a valid key pair. So, of course, obviously, a clone device could easily have a valid key pair, and you need a way to eliminate that device from receiving the CS or generating a CSR and receiving a certificate. So you need to, in your provisioning service, you need to have a way to confirm the identity of the device requesting the CSR before you actually allow the CSR to proceed. And if you really want your device to have a pre-burned unique device ID as well as a pre-burned key pair. Having talked about these generic approaches and issues, I want to jump into a specific implementation. As we mentioned earlier, this implementation is based on the one hand for the actual IoT device on the SimpleLink Wi-Fi MCU, which is a dual-core MCU. It has an application processor in there and also has a separate network processor, which completely offloads all wireless networking and security operations, including secure storage, from the applications processor. And that SimpleLink MCU has in it a pre-burnt unique device ID and a pre-burnt public-private key that are placed there by TI when we manufacture the chip. To develop your application on the SimpleLink MCU, you use something called the SimpleLink SDK, and that's augmented by something called an AWS IoT plugin, which provides the necessary connectivity software and protocols to connect into AWS IoT Core for your standard device management and device telemetry operations. In addition, the next release of the AWS IoT plugin in a few weeks' time will be adding a provisioning code example, and that will include the code that generates the CSR and connects up to a provisioning service that runs on AWS Lambda. I'm going to let Rich Ehlberger later on go into the details of the AWS side, because there's quite a bit more to it than what I'm showing here. I'm going to jump down and show you a few more details on the device side. Now, before I jump to the next slide, there is one out-of-band operation that has to happen to make this provisioning process work. If you recall, the provisioning service needs to check, is the particular IoT device requesting the CSR an authorized device to join the network? So to do that, we need some type of database that has a list of unique device IDs and their associated public keys, so the provisioning service can check that database and authorize the device to receive CSR. So how's that done? When you receive your IoT devices back from your low-cost manufacturing partner, in your kind of final production test facility, you can use a tool called TI UniFlash. And TI UniFlash allows you to boot up a SimpleLink Wi-Fi based device, and then you can then connect to it via UART connection. And there's a special hook in the bootloader which now allows UniFlash to download a function. And we provide the code for this function, so you can go and download that down during your testing process and extract the unique device ID and public key. And then you simply pass those then, obviously, up to the testing environment. And then from there, the test environment, there's some other example code that shows you how to take the unique device ID and the key and enter it into a database, which is created up on the cloud using AWS's DynamoDB database. So at this point, before the ID device leaves your facility, you have captured the unique device ID and its public key, stored it in the cloud database. We then can look at the standard flow when your customer receives your IoT device. He's going to connect the IoT device to his network. It's going to boot up, and then the first thing it will do is try and generate and sign the CSR and send it to the provisioning service. So when it generates that CSR, which is supported by some built-in software on SimpleLink Wi-Fi, it gives the unique device ID as the name part of CSR, and then obviously includes its public key inside the CSR and signs it with the private key equivalent of the public key. At that point, the CSR goes up to the provisioning service. It can then, from that CSR, extracts the public key, extracts the unique device ID, and compares it against the DynamoDB database that was created earlier. If there's a match, it goes ahead, authorizes the CSR, sends down a client certificate. The SimpleLink Wi-Fi device now stores that client certificate in its secure file system, which is completely encrypted and prevents any unauthorized viewing of that certificate. And then it can go ahead and connect up to the standard AWS IoT core service, which will then request from the IoT device a certificate, the one you just stored there, to validate that it is authorized. At that point, we've successfully connected to the AWS IoT network. Now I'm going to hand over to Rich Ehlberger, who will then go through quite a few more details on the AWS side of the equation.
Hey, thanks, Nick. So I'm just going to go to the next slide here and look over this slide and the next slide relates to the device provisioning at runtime. We're going to talk mostly about the cloudy side elements within AWS that facilitate the process that Nick has already gone through at a high level. It's assumed that the list of the whitelisted devices that Nick talked about that need to be taken at manufacturing time, that they've been delivered to some kind of authorized individual. And that authorized individual has uploaded that data into what we consider a public key table. So we're going to have a pair, which is the serial ID and the public key. Now, the hash key in the DynamoDB database is the device serial number. So that's the lookup ID. And the data is the related public key. This is done before the product even hits the shelves. So this is pre-shipment time. Now, once the consumer buys the product and turns it on, it looks at the network processor that Nick was talking about and to see if there's been a certificate that's been persisted to the secure flash within the network processor. And if so, it would just connect directly to the device gateway within AWS IoT Core. But in this case, in this scenario that we're going to walk through, there isn't a certificate present, so it hits the API gateway endpoint, which is a REST endpoint to get the certificate. API gateway is a way that you can model REST operations up into the AWS cloud securely. So before it can get a certificate, though, we need to understand if this is a legitimate request. The way the system is implemented, we will compare the public keys. We already have the one that was set during the whitelisting process, which is up in DynamoDB. But how do we know the device serial number from this web transaction? How do we get the public key related to this request? When the CSR was constructed on the device, the CN value in the subject was set equal to the serial number that's set in the network processor. The authorizer code, that upper Lambda function, extracts this value from the CSR and uses it to look up the public key in the DynamoDB database, and if found, retrieves it. Now, if not, it will fail by responding to API gateway with the response code, which it will propagate back to the device. Otherwise, it extracts the public key from the signature applied from the CSR. And if the two public keys match, then it's an authorized device. So once it's identified as an authorized device, then we can issue the certificate, okay? So the response goes back to API Gateway. API Gateway says, hey, you're authorized. Now let's go issue the certificate. So it goes back and once it's identified, then we can issue the certificate. And in this case, we're going to issue the certificate from IoT Core. In the next slide, I'm going to show a slightly different, more global way of doing this. But in this case, we're just doing it in a single region within AWS. Now, what it does at this point is that it's going to issue that certificate using the CSR directly to AWS IoT Core. Now, AWS IoT Core itself has an intermediate CA that is managed at a regional level. So you can pass your CSR to AWS IoT Core, and then AWS IoT Core will issue a certificate. But in so doing, it also needs to create a few other items. Okay, the Lambda function is going to create the thing that enables customers, the thing object within IoT Core that enables customers to have a device shadow within IoT Core and also be able to enable them to do device management at scale, to use job management and so forth. So the policy itself is required because that's what actually governs the authorization for people to do actions like connect to AWS IoT Core, publish, and subscribe to topics. And so this certificate needs to be unique per device, but a policy itself doesn't have to. So you can abstract that with policy variables. So you can have a single policy for many devices for a given product that you're deploying that's built on top of AWS. Now, after that point, what we're going to do is take that certificate that was generated and then propagate that back to the device through API Gateway. So then it can actually take that certificate, that's a response, an HTTP response with the certificate payload, and it can then persist that to the flash within the network processor. Now, once that's done, it can connect directly to AWS IoT Core and automatically authorize and start doing work, ingest work, and publish and subscribe with AWS IoT Core itself. So what I'm going to talk about next, this process works well if you're operating within a single region, and AWS has many regions that operate worldwide. But if you're going to be taking a product and you want to actually sell that product globally, then something that you would want to look at is how to do a global deployment of your IoT devices. So your device will, if someone is using their device in North America and they happen to travel with it in Europe, that it's actually going to give them the same responsiveness responsiveness and user experience. In order to do that, you need to have the ability to propagate these certificates on a global basis. Now, many of these artifacts within this diagram are the same. They haven't changed from the previous slide, but there are a few new components here that I need to go through. So this initial transaction with the network processor and up into API gateway is exactly the same. Going to the Lambda authorizer is exactly the same, and looking up the public key detail is the same. But what's different on the right-hand side, I clicked through it a little bit quickly, is how you actually get the certificate authority put into place up into AWS. So in the previous slide, I talked about AWS IoT Core managing the intermediate CA. In this particular case, you're going to be leveraging a process called BYOC, or Bring Your Own Certificate. And the way that we can automate provisioning client certificates globally is by leveraging a service called AWS Certificate Management Private CA. By putting the CA that you're getting issued from your own HSM into the AWS cloud, you're able to automatically, through the cloud, provision these certificates in a mechanically similar way, but not the same way as what I discussed in the previous slide. So actually, after I authorize and get to the point of hitting the certificate issuer, now what I'm going to do is take the CSR that was pushed from the device, and I'm going to pass that along to ACM PCA and get that provision from ACM PCA. Once that's provisioned from ACM PCA back to the Lambda, then what I can do is take that same certificate and push that to AWS IoT Core and register that certificate with AWS IoT Core. The reason why I can do that is because that same CA that you got issued from your own internal intermediate CA, you can propagate that same CA worldwide, and that same client certificate can also be propagated worldwide. So you can use the same authentication mechanism in every single region where AWS IoT Core operates. Other than that, the same principles apply. We're going to register the certificate, and we're going to create the thing and the thing policy as if it hasn't been created already. Then after those constructs have been created and linked together, then we're going to take the certificate that was provisioned from ACM PCA, send that back to API gateway, and then eventually back to the device. The device puts it into the secure serialized flash, like what I discussed in the previous slide, and then it can connect directly to AWS IoT Core. Now, what's interesting about this point, when you're talking about a global deployment, is now what you can do is use a service like Route 53, where it can geographically determine what is the best endpoint for you to connect to. And then it will be transparent to the user what region they would actually be connected to, because those certificates would be propagated to every single region worldwide. So in the next slide here, what I'm going to talk about is actually the differences between some of these provisioning purposes. And I'm not going to go through each one of these boxes step by step. It's really, this chart is really here for your reference to determine for yourself what's the best mechanism that you want to use when you're provisioning your device. This process you can use with the process that I just discussed. You can also use just-in-time registration or just-in-time provisioning if you've done that with previous projects that you've used, that you've built on AWS. So those are all automated processes that you can use. The one that I discussed is one I did directly through Lambda, which actually makes it a little bit simpler. But it's really up to you which process that you actually feel most comfortable with. All those processes will actually work. But what you can see is that when you're provisioning with ACM PCA, it gives you the most flexibility in terms of global deployment and the types of provisioning technologies that you might want to use when you're deploying your solution on top of AWS. So the process that I talked about on the right-hand side of that diagram with the Lambda functions and the DynamoDB table and building all those provisioning objects is done with an open source project. named secret-free provisioning. And this is in a repository up on GitHub. The secret-free repository contains all the cloud-side components that are required to perform that process, to actually get all those components in place in the AWS cloud. The installation is automated using CloudFormation. And if you have any questions with specifically about the code or how to actually run the CloudFormation, feel free to ask those questions through the GitHub repository. And with that, I'm going to turn it back over to Nick to go through the end of the presentation.
Thanks, Rich. So to summarize, obviously IoT networks need the devices to have security credentials. They can be sure that only authorized devices can in fact join. So getting these credentials into the IoT device manufacturer is expensive. So TI and Amazon have put together an example of a CSR-based implementation, which provides ease of use, lower costs through the elimination of doing it during manufacturing, and the appropriate security by complementing the CSR process with a device identification database, which enables you to make sure that only authorized devices can join. So with that, I'd like to thank you for attending and throw in the presentation to questions.
Great. Well, a few of you have already submitted questions, so we're going to jump right in. If you'd like us to submit a question, type your question into the question window on the side of your screen and hit the submit button. While we're answering your questions, please complete the feedback form, which is located at the bottom of your screen. So for our first question, what choices of toolchain and RTOS do I have for developing applications on SimpleLink Wi-Fi to link with AWS?
The SimpleLink SDK contains both free RTOS and TI RTOS as two RTOS choices. And then for toolchains, we support TI's CodeComposer Studio, GCC, and also we support IAR. So there's a good selection of both OSs and toolchains for you to go ahead and develop applications with.
Okay. For the next question, can the ID simply be the MAC address of the Wi-Fi for an IoT device?
Yeah, so I can jump in on that one. And what I would say is it would be a little bit sketchy to do so. What we want to do is use an ID that's basically cannot be modified, right? The problem with a MAC address is that you can program a MAC address into a Wi-Fi controller. The serial ID is actually something that's programmed at manufacturing time. So we want to use something that actually can't be tainted in the process, so we can have accurate whitelisting.
Okay. Next question is, how does a SimpleLink Wi-Fi device communicate with AWS IoT for day-to-day operation?
It's Nick here. I'll take that. So I said the SimpleLink IoT plugin contains the appropriate software to do that. So essentially, there's a protocol called MQTT, which is generally used for all the publish-subscribe communications between the SimpleLink device and AWS IoT core. And the plugin provides that MQTT stack that then sits on top of the rest of the SimpleLink wireless networking stack, and that's how we communicate. And there's also some additional software required for, as Rich mentioned, there's a thing which exists up in the cloud that parallels the actual real device. And so we have the thing management also built into that plugin.
Well, that concludes today's presentation. On behalf of Electronic Design, I'd like to thank Texas Instruments and Amazon Web Services for sponsoring today's event, and of course to all of you for joining us. Have a great rest of the day.